Good to see you all. So my name is Josie West. I'm going to be talking about complex systems moving from digital twin to digital cognition, which is something that's been close to my heart for a long time. So I am the director of AI and IoT offerings at Avanade. It's a mouthful. My background has been in data science consultancy for about 10 years, and I've spent the whole of my career looking at lists of skills on a list of skills that a data science consultant has, and I don't have any of them. And it was only when I got later in my career that I realized, actually, there's a skill in debunking the buzzwords that we have in tech. Digital twin, metaverse, computer vision, AI, all of those things. It's all about what's the value in these products, in these technologies, in these approaches. So hopefully I'm going to do that for you today and talk about digital twin and digital cognition, which is a coined phrase that we've put together in Avanade. So quickly on Avanade, we are a child of Accenture and Microsoft. So about 20 years ago, Accenture and Microsoft came together and created Avanade. We're predominantly US-based, there's 60,000 of us. And our purpose is to advance the world through the power of people and the Microsoft ecosystem. So it's important to note that we work very much in the Microsoft space, and we work very, very closely with Accenture, so it's really good to be here today. So I'm going to talk to you about digital twin, which is probably a phrase you all have heard of. I'm sure that's why a lot of you are here. I'm going to talk about the journey that we've had so far with digital twin, possibly debunking a few of the buzzwords and what it really means in there. We'll talk about complex systems, something that's very relevant in today's world, and how we approach them at Avanade, looking at the entities that we model. I've just come from a great talk about ontology modeling, semantic knowledge graph. That means anything to anyone. That's what we'll be talking about a little bit there, without the buzzwords. And then we'll talk about the technology that we use and give you some real client examples that we're actually using this in industry. So first of all, let's talk about digital twin. Now, I've put the definition up there. As part of Avanade, we're part of an organization called the Digital Twin Consortium, and defining digital twin has taken a very long time. This is where they are at the moment, which was only 2020 that they sort of finalized the phrase. So a digital twin is a virtual representation of the real world. That's probably something that you've heard of before. It's the entities and the processes synchronized and at a specified frequency and fidelity. Now, I've underlined 3 words in there because they're important. First of all, frequency. Often people think that digital twin needs to be real time. It doesn't. It's a specified frequency that's relevant to the system that you're using. If you've got a digital twin of a building and you're just looking at how that building's structured and there's 5 floors, you don't need it to tell you every day that there's 5 floors, every second there's 5 floors. Now, if you're modeling the energy efficiency in there and the people moving out, then yes, real time might be a useful thing to have. So specified frequency. Fidelity, also very important. It's a digital twin, not a digital sister or a digital shadow. So the fidelity of, I'll come back to the shadow. The fidelity is about making sure that you trust the data. So it's replicating the real world, okay? It's not just a model that we think is relevant. It's replicating the real world. There's fidelity to it. And then back to that shadow example, synchronized. So when we think about digital twin, it's not just about a physical or a real world thing. Let's go back to building, and then a replica of that, and the data's coming from the thing to the replica, creating a shadow of it. It's going back the other way. So it's a digital twin. Now, lots of people, when they talk about digital twin, they talk about where it started. And if you've heard any talks about digital twin, they'll have referred to the fact that NASA originally coined the phrase of twinning. So it's been around a long time. Now, of course, I know that's not Friday 13. Of course, when they were looking at it in the past, they were using it for simulation. There wasn't a data connection between it. It was just a twin, in the loosest sense of terms, of the spacecraft. And they were able to model on the ground if they were to do something, what would happen in the spacecraft, right? Simulation that we all know about. As time moved on, we moved into Internet of Things, okay? So we started having sensors in these devices that created data. Now, this picture shows it goes one way. Of course, we know Internet of Things can go both ways, but essentially you're sharing that data to the internet so you can access it remotely. So when you're going home and you want to see if your house is warm, you check on your device. There's a sensor in your house that tells you how warm it is. Your device tells you how warm it is when you're on your way, and you can potentially interact with it and say, turn it on, I'm cold. And then we move into digital twins. Now, digital twins, first generation. So the Internet of Things sensors move from that thing in the real world into a replica in the virtual world. Now, it's not just the Internet of Things data, Internet of Things sensor data coming from that real world thing into this environment. It's creating a twin. So there's a static data here that's the data's pulsing through it and bringing it to life. If there's a light on in your building, your twin says that there's a light on your building on floor 3 in this area of the building, right? You've got the static model that the data is sort of lighting up. But digital twin technology is much more advanced than how we use it today. So we're calling it second generation. Now, we're talking a lot about Azure digital twin in this instance, the technology itself. But there's a capability to model the asset properties, so the states of that asset, the processes within it, the resources that are required for those processes. And I'm going to come back to that. But essentially, digital twin's been on a long journey, okay? It's gone through all of these sort of different stages, and I'm simplifying it massively. But as time goes on, the important thing is real-world accuracy increases. So as we get more advanced in our technology, we're always trying to get it more accurate to the real world, or more relevant is probably a better use of the term. But what's the value? Digital twin is often talked about in manufacturing, smart factories, smart buildings. Okay, there's value in that because you might want to automate your systems, you want to know what's going on in your systems. But outside of that, interestingly, when you look at the Digital Twin Consortium, when you ask people to give real client examples, it gets hard. That difference from the sort of techie world into the business, real life, what does it mean for the client world, is often hard. But you can think about it in a different way. So if I gave you an address in the city now, I mean, some of you know the city a lot better than I do, as you can tell from my accent, but you would probably go to your phone and you would put in your phone the address into Google Maps. I hope Microsoft aren't watching this because it's not Microsoft. But Google Maps is an application in its simplest form with a network of roads that we all use to either walk to or drive to or cycle to a destination. That is a digital twin of the real world. The network of the roads is your static data. And as we move along with our phones, there's GPS signals on our phones, sending a signal up to an Internet of Things device, and it's saying, you're at this point on that road, but it's also telling you how much traffic is up ahead because other people, other things are also on that road, okay? It's a digital twin. Whether they use digital twin technology or not is irrelevant, but the definition of a digital twin is Google Maps. Now, the value is getting from A to B, okay? We're getting from A to B and we want to get there the fastest. So it brings up that information that it knows from its static data. How long does it take to go on this road? And the streaming data that comes through, and it tells you how fast it gets to A to B. But while you're going along that route, it's constantly challenging and questioning how fast can we go from A to B. And when you go along on your bicycle or you're walking along, it will suddenly say, there's a route that's quicker. So it's constantly running that KPI of time between A and B. Okay, the data science within your digital twin is very important. Now, you'll also find that that Google Maps has started doing a little eco sign on it, right? What's the most carbon efficient route? Now, I don't know what the data is behind it. I haven't looked into it. But each of the entities or the steps on your route in your digital twin initially had time as the KPI, but you can introduce other KPIs into it. And you can see how digital twins can start to advance. Now we've done that, let's talk about complex systems. And before I get onto the complex systems, I want to talk about complicated systems. Complicated systems have many moving parts, but they operate in patterned ways. Buildings are complicated. If you think of a building, this building, it's a structure and it's got multiple systems and subsystems within it. Piping, electricity, and the people moving in and out of the building. But if we study the blueprint of the building, we can predict what's going to happen with it. Complex systems are very different. Whilst they operate in the patterned ways, the interactions and elements between them, the relationships, are constantly changing. Cities are complex. Cities are made up of buildings and what happens within those buildings, if that's useful, but also traffic and people flowing in and out of that building. When we go to a zebra crossing, do you use that term? A pedestrian crossing, and you press the button on your crossing, how does that impact the traffic 200 meters up the road? Okay, that complex system, it's very hard to understand the behavior and predict the behavior without really significant studying, data, and simulation. Why is it important? Because complex systems are all around us. It's very, very relevant when we start talking to our clients, supply chains and their fragility, organizations' carbon footprint, we've talked a lot about today, sustainability in general, transport systems, energy. All of this is examples of complex systems, and there's a global need to really start to understand this. So how do we do it? How do we start looking at these complex systems? Now, the first thing is most complex systems are massive, and it's really important that we go step by step. We don't try and bore the ocean. I'm going to take you through a little bit around the tech and approach to data that we use to model these complex systems and better understand them, starting with those entities. So traditionally, we've looked at data in that sort of tabular format. When we look at complex systems, we need to start looking at entity-based modeling instead. Now, when we think about a complex system compared to what we normally look at with digital twins, it's not just the assets alone. It's not just the building as the asset, that physical structure that stays there. Now, an asset is your physical or virtual, doesn't need to be physical, it can be virtual, component that's vital to achieving the value. In addition to that asset, as you can see, you've got processes, which is a task or a set of tasks that transform the asset from one state to another state. I'll give you an example in a minute. And then resources. They are required by the process to complete the task, state transition on an asset. Now, let me give you an example, okay? At an airport, a plane leaving, easy example. Most of us have been on a plane, or we know what happens on a plane. The plane is the asset. The first state is the plane is not ready to leave. The final state is the plane is ready to leave. Now, there's loads of steps that happen within that, between those two states. Processes like loading baggage, loading passengers, and doing the safety checks. The resources required to do it, baggage loading equipment and assets, check-in staff, safety checks, safety officers that do the safety checks. All of those resources are required to complete those processes that will transform the asset from one state to another state. Why do we do this? Because we get a machine-led diagnosis when we model it. So, if we collect all of that data, the plane and the time that it left, the baggage handlers and them checking into their rota, and then that the plane left late. We can take all of that data and we can put it on a dashboard, and as a human, I can look at that dashboard and I can say, the plane left late on a Monday and there was no baggage handling staff, so we need to improve the baggage handling staff on a Monday. I've diagnosed that. If we model the entities in asset, process, and resource, the system, your digital twin, can tell you why the plane left late. Okay, there's an element of causality modeling within there, of course, but by clarifying if it's an asset, a process, or resource, you can start to understand why the plane left late. or indeed left early. We don't care about that as much. Now I'm going to flash this up, not go to it in too much detail, okay, but finite state machines. Now that process was one small, quite obvious example. It doesn't really matter when the bags are loaded, when the passengers are loaded. Probably matters when the safety check happens. But with a finite state machine, you can see an example of the starting state of an asset and the end state of an asset. Now this is using something like a supply chain, what we call the traveling salesperson example. But the steps can be many different routes, okay? There's lots of different routes on that process. And as you can see, as you move from, let's go from start to C to E to H to E to the end, there's properties within each of those relationships that can collect as it goes through. And you can start to see, back to the Google Maps example, when you get to the end, you've potentially got accumulated lead time, accumulated cost, accumulated carbon value, for example. Whatever the KPI is you want to model and understand, you can build into that process, that finite state machine, which is essentially the model of your process. Now, I can't do it, but if we were to turn that on its side, underneath each of those states, you've got resources and you've got assets within them, okay? And it's all interlinked within your complex system. The example I gave you was a plane leaving on time and a few processes and a few assets within it. But of course, we all know that what impacts a plane leaving on time is lots of different things. Okay, the staff at check-in, travel disruption externally outside of the airport, departure lounge spend getting stuck in the departure lounge, will that impact the time the passenger arrives at the plane? There's many different things that happen in a complex system that machine-led diagnosis is really important. And of course, when you want to start understanding more about your process and the KPIs within it, Google Maps, then you can start to build up this graph. And this is that semantic knowledge graph. Now, if people know much about ontology modeling and semantic knowledge graphs, you'll recognize what I mean by this. But essentially, it's a completely different way of modeling data that we do today. And organizations really need to move in that way. It's fantastic to see a talk on it in the data room just a moment ago. So moving on to the technology, I want to start by explaining a definition of cognition. I've talked about digital twin a lot because it's a term that we all know, but we're using this term cognition because digital twin isn't really enough for what businesses need. Cognition, the action of acquiring knowledge, understanding and learning through thought, experience, and the senses, okay? Senses, change it to senses, knowing what's happening, how we're feeling today, right? The senses, our senses. Experience, what's happened in the past. And then thought, we're thinking about all those things and what might happen in the future. Cognition is much more important when it comes to complex systems. And the technology itself, when we just look at digital twin, we use the analogy of a human body. It's our digital nervous system. It's our senses of what's going on right now. Now, Azure digital twin technology, and my technical knowledge probably doesn't go deep enough to talk about all of the other digital twin technologies that are out there, but actually the capability of the Azure digital twin, the history and the data science element is very small. It doesn't hold that much information. It's really just looking at what's happening now, current situation, digital twin. Your digital nervous system, what's going on. Alongside your digital twin, you need to think about your data platform, your digital memory, okay? Quality data, governance that sits on top of it, but your data platform stores that history, that experience to be able to understand what's going on today, is it normal? And then finally, and probably the most important, is the data science, right? Our digital brain. So what are we looking at? The future, taking the history of what's happened in the past, taking what's happening now, and looking forward to see what would happen in the future with that system. Now, the modeling is important. You'll see on the top there, the ontology modeling, that semantic definition of the business system. That includes both assets and resources. And the finite state machine, which I talked about, which is all about your processes. So your semantic definition of the processes. So let's talk about some real client examples and bring this to life a little bit. So the benefits that we see, there's many, and often we find when we talk to our clients, there's so many that they can get a bit too excited or it can confuse them, okay? It's not as simple as just taking one step and getting one reward. There's lots of different routes, so it's important that we validate these and make sure we have a very key message when we talk to our clients. But of course, decision making, so connecting all of that data and having it at the right time to make a decision. We talk about nudge economics a lot when we talk about digital twin. Decision making is about giving the right information at the right time. Now, ontology modeling and semantic data graphs, knowledge graphs, mean that you can understand, the machine can talk to each other, you can create these sort of autonomous systems. Yes, that's a benefit, that's a value, but ultimately often humans need to have a nudge rather than a decision being made for them. The Google Maps example. It doesn't tell you to go down that route, it just tells you there is a quicker route, do you want to take it? Situational awareness, helping people understand their whole system, that macro scale of a system, the complex system, and seeing it. If you think about the airport example, you can see how things are happening on the aprons in an airport. An apron's where the plane sits, for those of you that don't know. Collaboration and interoperability. I haven't talked about this that much, but being able to share data is very important, and digital twins and ontology modeling can create a very useful and easy way to share data. And then finally, and most importantly, trust in data. You have to be able to trust the data that's coming through. It has to be a digital twin, not a model, not that shadow. So making sure that you trust in that data. We're talking about this with smart organizations, carbon reporting, supply chain, and of course, I'm in the metaverse room, which is shiny and exciting. Metaverse ready. All of the presentations I've seen today have been very inspirational about metaverse and about, headsets, VR, XR, 3D environments. Without the data, it's not going to be very useful, okay? When you start thinking about the metaverse, when we go into environments where we can collaborate and work together, it's not really about the visualization. It's about the data that we are all able to access at the same time in that entity-based modeling. That's really important, and that's the conversations that we're often having when we talk about metaverse. We try and rein people in, stop them thinking about, headsets. We will get there, but we need to make sure that the steps that they're taking is worth that investment. Now, I'm going to give you a couple of examples. The renewable ones is a more detailed example. But I'm going to start with the water industry company. I can't talk about who the client is, but I want to give you an example of a complex system that isn't as big and huge as supply chain or carbon in organizations. The health of a river is a complex system. Now, in the UK, there's a lot of media about the health of the river and the things that organizations are pumping into these rivers, so they're really interested in understanding more about it. Now, this water company knows all about the health of a river, and if you and I went onto Bing, Microsoft Bing, to Google the health of a river, we might be able to draw a very simple graph. Oh, you can't see that easily, so apologies for that. But we went into this water industry company and we asked them to talk about the health of a river. We needed to draw what would be the first instance of an ontology. I'm not going to go through all of the detail, but ultimately, river health is at the bottom, and there's many different routes that would go down to the river health, okay? Abstraction, discharge, the weather, what happens outside of what they have control of, the physical modification of the river, the flow within it, the biodiversity, which ultimately means the health of the river. It's a complex system, okay? It's not just one-way directional, there's multiple routes in there, and to be able to understand it, we need to model it in a completely different way. Now, that just gives you an idea of, at the start of an ontology, that wasn't quite an ontology, but the start of an ontology, how we start with clients, and giving an example outside of just the airport or the concept of ontologies. SSE Renewables is one of our biggest clients in the UK. They are an energy company, and they own lots of offshore and onshore wind farms, amongst other things. And if any of you have ever been to an onshore wind farm, they're actually really dangerous. So they're often in really remote places. with extreme weather, and when an engineer goes on site, the organization needs to make sure that they are safe. I mean, it's like possible risk to life kind of safe, okay? So they came to us and tried to ask us how we could really model and understand where their engineers are at that high level. So what we did was we built a digital twin of their wind farm. Now, this is an example of a device that would be used by an engineer, and this is an example of the dashboard that we built. All of it's underpinned by digital twin. So the resource, the engineer, hopefully this will start playing, you can see has moved from outside the geofence inside, and that was done on a separate application. But as it moves on the location on here, it shows it on the map. So you've got that system going both ways. It's connected to that digital twin, and you may have seen there an alert came up to say something's happened, okay? So it's one-way connected. The dashboard allows two different views, of course, depending on the user, you'd have different views of that dashboard, but you can move into another example, and you can see the alert. So once you look into the alerts or the alarms in a different way, you can then understand what's going on, and you can acknowledge that alert, and it will appear onto the device, okay? Synchronized, two-way directional between the digital twin. All of that information, as I said, is stored within the digital twin. So when we have a field engineer that comes on site, it will appear on the digital twin. Each of those elements is part of that wind farm, the turbine, the field engineer, the asset, the process, the resource, is defined within that digital twin. And as you can see, it talks through all of these. And this is a digital twin visualizer. It's really hard to understand, okay? You and I would look at that and think, cool, what are you going to do with it, okay? But it's very complex. It's differentiated between your assets, your processes, your resource. But as a client, it's really difficult to understand, okay? So we need to bring it to life. Now, we have used a bit of mixed reality. But what we've done is bringing that digital twin to life away from the dashboard that people are used to and into something that's a little bit more holistic. We've used Unity, and you saw there a little man moving, an engineer moving into the environment. You could follow him as he was moving from your device. It appears into the twin, it appears in Unity. But then also each of your assets have information stored within the twin. So you can click on that asset and not just understand what's going on, but you can simulate. So you can change the direction of the blade, you can change the rotation of it, and actually, I'm not sure if this video shows it, but you can also simulate wind within it. So you can start to see how that system will react when you start simulating these environments. So you can simulate as well as understand what's going on in real time. Now, of course, there's other views of this environment, and sometimes, depending on who you are and how you're using it, you need to see it at a more macro level. So you can see here that you can zoom out and understand more about that. So we're not thinking about the engineer anymore, we're thinking about the behavior of these wind turbines. Now, because we put in the processes, we've got all the work orders that are associated with that process. And as you can go through those work orders, you can see the turbines are lighting up as blue. You can zoom into those, and you can understand more about what's going on, what's the problem, and start to diagnose it. So if you're an operational engineer and she's sitting there and understanding more about how this looks in the wind turbine, why they blew, she can then go into the process and understand at what point of that process they are, so how it's impacting it. So that's really just a very early example, or sort of high-level example of where this comes into play. But really the power is when we connect data. Connecting data is difficult if you don't have that semantic level of modeling. So a filter is a filter, okay? If you're different languages of a filter, you need to make sure that you're connecting data in a way that's comparable. But also, if you build these digital twin environments, you can have twin of twins. So you can have a twin of your plane, and then that feeds into a twin of your airport. The Digital Twin Consortium is talking about all kinds of national digital twin programs, for example, where we're building these twins of twins. But you have to model your data in a very different way. It has to have that semantic definition. Now I'm going to leave with a video, and then I'll ask questions. answer any questions.
In the last video, we explained the concept of digital cognition and how it can create a powerful solution to help the performance of your business. In this video, we're going to demonstrate digital cognition in practice using the example of a busy airport. We're all too familiar with the issues that can occur, things such as limited parking availability, multiple requirements to check in, significant delays through passport control and security, walking distances to the gate taking longer than we realise, and after the flight, we get to our destination, yet more queues at passport control, often followed by luggage delays, and that's just for the passengers.
Additional high-priority issues for the airport also include traffic jams and rail delays into the airport, creating a smooth enough flow to allow passengers to shop in the retail areas, flights leaving on time, delays to incoming flights causing unexpected peaks in demand, allocating gates in a timely manner for all incoming flights. Get any of these wrong and it's likely to result in revenue loss and service level issues.
But many of these situations can be avoided or at least minimised. Machines can spot trends and suggest remedies to situations before they become problematic. Staff can be nudged to make changes that will alleviate problems before they grow.
Let's look at what happens when there's a problem with the transport network serving the airport. Typically, the airport is unaware until a noticeable number of passengers arrive late to check-in. Unless they're rushed through check-in and security, many people could even miss their flight. And even then, there'll be no time to use the retail facilities, meaning trading revenue will be affected. And if the number of late arrivals is big enough, the flight is likely to be delayed. All of these things create stress for both the passengers and staff and impact the profitability of the airport. But this can be avoided when combining many data sources, monitoring their status, and using automation to take action when needed.
Data extracted from the transport networks allows us to calculate the number of passengers due to arrive late, along with how late they're likely to be. We can then predict queuing times for each stage of the journey through the airport, how much revenue will be lost from the retail area, how many flights may need to be delayed, and the resulting financial penalties for these delays. These predictions quantify the problem in business terms and provide context to the proposed remedies. How many staff are required to improve this solution, where to deploy them, and quantify the level of improvement per head of staff added. The projected additional cost to the airport can be shown against the potential loss if nothing is done. It may be some delay is preferable because it produces the best balance between increased queuing time and additional costs.
Armed with this information, the airport managers can make good decisions quickly to keep passenger flows moving within acceptable cost ranges. But it's not just airport managers that receive alerts from the AI. Staff on the front line can be nudged within a range of predetermined parameters to keep things on track.
Not all situations need human assistance to run at their best. A good example of this is airport parking charges. The goal is to optimize the price and generate the most revenue, but that's difficult when demand fluctuates throughout the year. Analyzing previous sales history enables the AI to calculate prices and then measure its own success. By trialing minor variations, it can identify whether the model is pricing too high or too low for any given week of the year, and then adjust accordingly. It will take account of weather, national and school holidays, as well as a range of other factors.
Within a few weeks, the AI will have spotted trends that the human brains can identify, and within a year or two, it will have increased revenue consistently for every week of the year. As well as setting the pricing, it can suggest greener transportation links personalised to each passenger. These can be included in automated promotional activity, targeted at relevant demographics and driving demand when needed. When you apply this approach to the many and complicated processes running the airport, the uplift in performance is significant. Each part of the airport sees benefit, and these range from service levels, staff satisfaction, productivity, and profitability. The creation of a model and its integration into everyday processes introduces a platform that can be revised and enhanced as practices change. Over time, the advantages enjoyed by a digitally cognitive airport versus those without automation will be significant. In a competitive market, being left behind is not an attractive proposition. Of course, it's not just airports that can benefit. Processes applicable to every type of business can be enhanced and performance improved.
To find out what this means for your business, get in touch. We'd love to hear from you.
Now that was a very salesy video, but it gives you an example of a system that has multiple data coming through, and that was based on one of our clients that we have at the moment. Thank you for listening. Any questions?
See one gentleman, they're over there. Focus. Give her a round of applause. Josie West. If my flight is delayed this evening, I'll say you didn't listen to Josie West. There you go. We still have time for one or two. What are the most problematic areas on current momentum in digital twin development?
Ooh.
There you go. Bam.
Oh, God, that's a great question.
Do you want to call a friend?
So, I think the problem really is that there is a lot of the tech community are talking about digital twins, but in practice, there's not many digital twins that are actually in operation. So, whilst the tech community is moving forward with digital twins and thinking about all these new ways to do it, I mean, which is what we're doing in digital cognition. But it's very much defined about the theory of digital twin and what it means. And there's lots of thinking around that, that hype graph that Gartner talks about. Actually, there's not much in operation. The type of digital twin that's in operation is really manufacturing. So we're not getting real feedback from the community that are using it. I think that's probably the biggest sort of problem that we're finding. I also, one of the key areas is the sensor data and relying on that sensor data. Now, if you think about, I was talking to a client last week around sensors on the network, the sort of energy network within the UK, and they know that all of those sensors are out of sync, that they're wrong, the data's wrong. So that fidelity is one of the biggest problems in making sure that you have got a twin, not a replica. Okay,
we have a new, oh, there it goes. I wanted to say we have a new winner of a question, but it popped away. Where are we here? How stop pushing the buttons. How long does it usually take to create a complex system that is based on digital twins?
So not long. The most of the work is paper-based. It's with the organization. So that example of the health of the river, that was a couple of weeks really to write up what we found in the workshop with them. But within Avanade, we've built a couple of assets that essentially you can turn a model into an ontology very quickly and fire up a digital twin. So your 4 weeks can move from that paper-based into that digital twin in terms of the tech. The complex system part is important because if you're looking at doing your whole complex system, it's going to take years, really going to take a long time. So you need to make sure that you're stepping on that bit by bit. And every time you step through that journey with a client in that real example, they have to have value at every stage. It's like the metaverse. It's going to take a long time to get there, but you need to have incremental value. So in terms of technically, it's easy. There's a big phase at the beginning, which is the paper-based, the business understanding of their ontology, but also process. If you take away the kind of subjective elements of process and you turn it into a codified process, that's quite difficult to have those conversations with people, just because what you often end up having conversations is that their role in the business isn't really a role. So you're having to sort of move from that because it doesn't really mean anything in the data world, in the coding world. So technically it's quick, but it's a challenge for that business conversation.
All right, and last one, how are you collecting your data?
All that, I mean, that really depends on the use case that we're looking at. I mean, IoT devices, of course, but it's not just about IoT devices. I mean, we do a lot of work in computer vision. SSE, the same client, we've got video feeds that are looking at puffins on the wind farm, and they're pulling that data from the video stream and doing some computer vision data science within that to count and monitor the puffins. So that's too big a question to answer, unfortunately, but always, it doesn't need to be IoT.
There you go, Open Slava 2023. Big thanks, well, gentleman in the front is taking a sales call. Very much thanks. Josie West, give her a round of applause. Thank you for sharing.